Recently, we've seen that matrix factorizations play an important role in linear algebra. For example, we use the LU factorization to help us solve systems of equations quite easily. In this video, we're going to talk about a different type of factorization known as the QR factorization of a matrix. Now, before we state exactly what the QR factorization is, I'm going to state a useful fact about matrices whose columns are orthonormal. So let's suppose we have a matrix Q that has n columns, and each of the column vectors u1 up through un is a vector in Rm, and we're going to assume that the vectors are orthonormal. That means if I take the dot product of any two different column vectors, I get 0, unless I'm dotting the column vector with itself, in which case I get 1. That's because it's the columns are orthonormal. Keep in mind that when I take ui dotted with uj, that's the same as treating u sub I as a matrix, taking its transpose and multiplying by uj. This would be then a 1 by m matrix. This would be an m by 1 matrix, so the product would be a scalar. Now, the useful fact is that if we have a matrix of this form and we multiply Q transpose times Q, we get the n by n identity matrix. Let's just check the dimensions. Q is m by n because it's made up of n vectors, each having m components. Q transpose, therefore, is n by m, so the product of the two should be a square matrix of dimension n by n. So why does this useful fact hold? Well, let's take Q and write it as u1 up through un. Now, when we take the transpose, these column vectors become row vectors as we've seen previously. So in other words, Q transpose is u1 transpose, u2 transpose, so on and so forth. So u1 was a column vector, now it becomes a row vector, and so on and so forth. So let's take Q transpose and multiply it by Q. So the rows of Q transpose are u1 transpose, u2 transpose, so on and so forth. And then Q has columns u1, u2 up through un. Now, this is really a big matrix, as is this, but think about this as a vector, an n by 1 vector multiplied by a 1 by n vector. The way you would do that is you would take all possible products of entries here times all possible entries of products there. So for example, the first entry would be u1 transpose times u1, which would be right there. That's going to be a number. The second entry would be u1 transpose times u2, which I'll put right there. That would be a number. And so on and so forth. The last entry in the top row would be u1 transpose times un, which is a number. And I'd play this game over and over again when I go from one row to the next. So for example, in the next row, I'd have u2 transpose times u1, u2 transpose times u2, and so on and so forth. And the very bottom right entry in the matrix would be un transpose times un, which I've written down here. But here's the thing, these vectors are orthonormal. That means that if I take any two different vectors, their dot product, which is represented by matrix product, is 0. So u1 dotted with itself is 1. u1 dotted with u2 is 0, and so on and so forth. u2 dotted with u1 is 0. u2 dotted with u2 is 1. And so when we simplify all this, we get nothing more than a matrix with 1s along the diagonal, 0s elsewhere. It's n by n, so it is the n by n identity matrix. So here's what the QR factorization says. Suppose that A is an m by n matrix with linearly independent columns. Then there exists an m by n matrix Q whose columns are orthonormal and an upper triangular matrix R that is invertible and has positive entries along the diagonal. And the factorization A equals Q times R holds. So we need to come up, this is a constructive proof, we need to come up, given our matrix A that is m by n and has linear independent columns, we need to find a matrix Q of size m by n, whose columns are orthonormal, and we need to find an upper triangular matrix R that is invertible and has positive entries along its diagonals. So the way we're going to do this is we're going to apply the Gramschmidt process to the columns of A. So I'm going to write the column vectors of A as W1 up through Wn. So there's n of these vectors. Each of these vectors is in m-dimensional space. Now, how do we get an orthogonal basis from these column vectors? Well, the Gramschmidt process says we first set V1 to W1. To get V2, we take W2, subtract from it the projection of W2 onto V2. No, that should be the projection of W2 onto V1. So we have W2 minus the dot product of W2 with V1 over the length of V1 squared, and all of this scalar is multiplied by V1. V3, similarly, V3 would be W3 minus the dot product of W3 and V1 divided by the length of V1 squared. That's a scalar. We multiply that scalar by the vector V1. And then we take W3, dot it with V2, divide by the length of V2 squared, and take that scalar and multiply it by V2, and so on and so forth. So in general, V sub k will be W sub k minus a sum starting at 1 and going up through k minus 1, where we take W sub j, dot it with V sub j, divide by the length of V sub j squared, and multiply this scalar times the vector Vj. Now, what's really important to realize, looking at this formula, is that each of the vectors, W sub k, in our original set of linear independent vectors is a linear combination of the vectors v1 up through vk. So, for example, W1 is obviously a linear combination of V1. W2, if we were to take this expression and add all of this to the other side, I would be able to say that W2 is V2 plus a scalar times V1. So W2 is a linear combination of V1 and V2. If I was to look at this line, and if I was to add this expression over to the left and add this expression over to the left, I'd have on the left V3 plus a scalar times V2 plus a scalar times V1 equals W3. So each of these vectors W, the original column vectors of A, is always going to be a linear combination of V1 up through Vk. And because I get the orthonormal basis by normalizing each of these, because Wk is a linear combination of these, and because each of the normalized versions of these just differs by a scalar, what this says then is that each of the vectors Wk in our original matrix, the column vector in our original matrix, is a linear combination of the orthonormal basis vectors u1 up through u sub k. So for example, W1 is going to be a linear combination of just u1. W2 is a linear combination of u1 and u2. W3 is a linear combination of u1, u2, u3. So we can express that a little bit more compactly by introducing constants for weights. So Wk is going to be a constant times u1 plus a constant times u2. I'm going to use a 1 here, so it corresponds to u1 and u2, and I'm going to use a k here to correspond to the fact that I'm looking at w sub k. So for example, W1 would be C11U1. W2 would be C12U1 plus C22U2. W3 would be C13U1 plus C23U2 plus C33U3, and so on and so forth. So W4 would be a linear combination of U1, U2, U3, U4. W5 would be a linear combination of U1, U2, U3, U4, and U5. So here's how we're going to define our matrix Q. Q is going to be made up of these orthonormal basis vectors that we obtain using the Gramschmidt process. Each of these vectors is in Rm, and there are n of them, so Q is an m by m matrix. Now here's how we get R. It's a little trickier. We're going to get R by taking these constants from above. So for example, to get this entry, these top two entries, I use C11, C12, C11, C12, which is right there, and then C13 as well, going all the way down. To get the next row, I leave a 0 here, then I use C22, which we saw right there, and then C23, which we saw right there, and so on and so forth. Now, this matrix is obviously upper triangular. The diagonal entries are C11, C22, up through CNN. Now, when we look at this linear combination formula, this term always has to be non-zero, and we can make it positive if we'd like, simply by switching the sign of this. So that means then that for all intents and purposes, we can assume that the diagonal entries are all strictly positive, which means that the determinant of this matrix is the product of the diagonal and is not zero, so by the invertible matrix theorem, this matrix is invertible, and it's of dimension n by n. If we take Q and we multiply it by R, so think about this, even though this is a matrix, think about this as a row vector. If I took this row vector times that column, the only thing that would be left, if I was to do that, the only thing that would be left would be C11 U1, which is right there. If I multiply this times the second column, I would have U1 times C12 plus U2 times C22 plus a bunch of nothings because I have a whole bunch of zeros here. That's my second entry. In the next column, I'd have U1, U2, U3, and the constants would be C1, 3, C2, 3, C3, 3, but that's going to give me just W3 right here. And so what happens is that this is W1, this is W2, W3, and so on and so forth up through W sub n. So when we multiply Q times R, we get this, but that's just A. So we have a factorization formula, QR equals A. We know how to get the matrix Q. We take the column vectors of A and we perform Gramschmidt to get an orthonormal basis for the column space. But now we have to figure out how to get R. This is really cool. So how do we get R? Let's take A equal QR and multiply each side by Q transpose. So Q transpose A equals Q transpose times QR. But we know from our useful fact, at the very beginning of the video, that Q transpose times Q is the identity matrix because its columns are orthonormal to one another. Okay, so we get R. So that means that once we start with A, we perform Gram-Schmidt to construct our matrix Q, and then R would simply be Q transpose times A. Here's an example. Here is a 4x3 matrix whose columns are given as follows. In a previous video, I showed how we could take those vectors, column vectors, W1, W2, W3, and perform Gram-Schmidt to get new vectors, orthonormal vectors, U1, U2, U3. I'll let you stare at the entries here for a moment. And I should point out that this is, these are all, make sure I have that right. Yes, these are all 1/2, 1/2, negative. Yeah, those are all correct. So that's my Q. My R then would be simply Q transpose times A. And if you compute that, I did it using a computer algebra system, this is what you get for R. It's 3x3. So R is 3x3, Q transpose A. And we notice how R is upper triangular and it has positive entries along the diagonal. Now, this factorization formula might not seem very useful, but it will prove very useful when we discuss least squares problems in linear regression.